Hi and welcome to this clip going through the weak acids questions I set for homework. I'm doing a quick clip on them because I didn't have time to go through them in class because we were doing our pH curves practical. But seeing as I've set them for you, I thought I'd pop them onto YouTube so we should have a little look at. So some of them are quite straightforward, like number one, it's obviously just definitions, and others are a bit more demanding. So we'll take them as they come, and I've also done it because the mark scheme that came with it was a little bit abbreviated in places, so it was abbreviated down for examiner's benefit, but maybe it's not quite so easily distinguishable for students, so I thought the video might help a little bit. So first of all, defining a Bronsted-Lowry acid, it's quite straightforward. It's basically a proton donor. So obviously proton is the same as an H plus ion, so you could put H plus donor as well. And weak acid, it partially dissociates. It's important to say that it partially or doesn't fully dissociate. And because it's an acid, it has to have releasing H plus in that sentence somewhere as well. So, moving the page down a little bit, it says nitric acid is sold by a chemical supplier as a 65% solution by mass. And it says, as supplied, each cubic centimetre of this nitric acid has a mass of 1400 grams. It's asking you to calculate the pH of this solution. So, to understand the question fully, you need to remember that it's a strong acid, nitric acid, so it will fully dissociate. And to calculate the pH, you have to get the H plus concentration. So, notice that it says each cubic decimetre of this nitric acid has a mass of 1400 grams. Now, because we want the H plus concentration in moles per decimetre cubed, and it already says that each cubic decimetre of the nitric acid has a mass of 1400 grams, working out the moles of nitric acid will give us this automatically. But we need to also remember that only 65% of the solution is actually nitric acid. So working that out gives us 910 grams of pure nitric acid in the solution. So that gives us 14.4 moles by dividing mass over molar mass. So remembering that the number of moles of hydrogen ions is equal to the number of moles of HNO3, and that the values were quoted as per each cubic centimetre, or sorry, decimetre, in other words per dm cubed, we can work out the pH as minus 1.16. So moving on to question number 3. It says, when nitric acid is added to methanoic acid, the acid-base equilibrium is set up, and they give you the equation. So obviously this is two acids reacting with each other, but one is going to be stronger than the other. So that means that the stronger acid will take the acidic role, and the weaker acid, in this case methanoic, will take the base role. So the acid on the reactant side always takes the role of acid 1. So looking for the species on the right-hand side that this turns into once the H plus is lost, we find the NO3 minus. So acid 1 and base 1 are interconvertible by the exchange of a proton. So if you look at acid 1 and base 1, you can change them over between one another by the exchange of one proton. So that means you can deduce what base 2 is and what base 2 and acid 2 are. So HCOOH and HCOOH2 plus will interconvert by exchange of a proton. So we can write in those pairings like that. Usually they'll allow you to write A1, B2, B1 and A2 in the right places on the equation. So let's go on to the next question. So moving the page down, this is a longer answer question. You can see by the amount of space that's been given. So 8 marks are on offer. So we can see that there's some data given to us, and that means we can use the data moles, equation moles answer to do the calculation part. That's a technique that we can revisit. Now, we don't have an equation as such, but we do have the data we can use to work out the number of moles. So what you do is you put your unknown compound A above the data moles, equation moles answer, do it like a table almost, and you can put in the NaOH to the right a little bit, and we can now write in the data. So we can work out the number of moles for NaOH. Now, just knowing at this point that the amount of A is 2.580 grams in 250 centimeters cubed, we have no idea how to approach the number of moles of A, but we can get the number of moles of NaOH. So that would mean we have the moles of OH minus now. So we go back to the new piece of information. Each molecule of A has one acidic hydrogen atom, and A behaves as a monoprotic or monobasic acid. And if we remember that H plus and OH minus react in a 1-to-1 ratio during neutralization, that means we can state that the number of moles of H plus, and therefore the number of moles of A, in 25 centimeters cubed is 2.999625 times 10 to the minus 3. But if we remember that the original solution was 250 centimeters cubed, we multiply that back up by 10 to tell us how many moles of A are present in the original 2.580 grams. So that gives us 86.0 grams per mole, because I've divided the mass by the moles to work out the molar mass of A. Now, there's quite a lot more to do, so I'm going to clear a bit of space. So we know the molar mass is 86 grams per mole. We know that it's unsaturated, and we know it's a carboxylic acid. Now, the carboxylic acid part accounts for 45 grams per mole. So the rest of it must add up to 41. So we've now got to try and work out what that might be. So I'm going to take a bit of a leap in the dark here, and I'm going to put in 3 carbons, because 3 carbons add up to 36. And obviously 5 hydrogens add up to 41. So now we have a possible structure. So we now have the molecular formula as well, C4H6O2, which we've been asked to do. And we've done a possible displayed or skeletal formula of the carboxylic acid. But it's not the only possible structure. But whatever structure you do come up with, it's got to have 86 grams per mole, it's got to be a carboxylic acid, and it's got to be unsaturated. So moving on to question 5. This time it's obviously about a pH curve. Now, you've done pH curves in your core practical today, and we're going to have a look at how this might come up in an exam question. So a student titrated the 1.5 times 10 to the minus 2 moles per decimeter cubed methanoic acid with aqueous sodium hydroxide. Then a 25 centimeter cube sample of the methanoic acid is placed in a conical flask, and the NaOH aqueous was added from burette until the pH no longer changed. So you'd be expected to recognize this as a weak acid strong base titration. The methanoic acid is obviously a weak acid because it's a carboxylic acid. And all carboxylic acids partially dissociate to a greater or lesser degree, so we call them weak acids. And you should know that sodium hydroxide is a strong base because it's got OH in it, therefore it behaves as an alkali. And all alkalis are strong bases. So remembering that methanoic acid is what we call a monobasic acid, it has one acidic hydrogen that it can give off. And remembering from earlier that H plus and OH minus react in a 1-to-1 ratio, it should be quite easy to construct an equation. Now you can put charges in, Na plus HCOO minus, but only do that if you put both the charges in. Don't put one charge in and leave the other one out, because then you're implying that sodium methanoate is a charged substance. It isn't, it's a neutral substance. And while I'm here, I've just realized I've forgotten to put the state symbol for water, so I'll pop that in now. So moving the page down slightly, they want you to calculate the concentration in moles per decimeter cubed of the aqueous sodium hydroxide. So if we extrapolate from the vertical section down to the volume axis, we know that the volume of sodium hydroxide is 30 centimeters cubed. So going back up to the top of the page, we can see that the data does not tell us the concentration. We have to work out the concentration, but what we can do is work out the moles of methanoic acid. So that gives us 3.75 times 10 to the minus 4 moles. So we can work out the concentration of sodium hydroxide by assuming you have the same number of moles of sodium hydroxide. And we know the volume is 30 centimetre cubed, so it has to be converted to decimeters cubed by dividing 30 over 1,000. So we do 3.75 times 10 to the minus 4 is the number of moles over 30 divided by 1,000. So bring the page down a bit so we can put that in. That gives us 0.0125. So the next part of the question asks us to calculate the pH of the aqueous sodium hydroxide. And it gives us Kw, even though this will be in the data sheet in any exams. So Kw is H plus times OH minus. So we know what OH minus is, we know what Kw is, all we now have to do is sub those in and rearrange. So that gives us 8 times 10 to the minus 13. So if we sub that into the pH expression, that gives us 12.1. So let's move the page down a bit. So to allow us to do this final part of the question, we need to have a look at the image of the pH curve from the previous page. So we need to decide which of the three indicators is suitable for this titration. So if you look at the vertical section, it's between pH 5 and pH 10. So the only possible one that we can choose is metacresol purple, and that's because its pH range coincides most effectively or closely with the vertical sectional equivalence point on the curve. So I've had to reduce the size of this page down a bit so we can see how many marks it is. We can see it's 5 marks. So I'm going to make it a bit bigger now so we can work our way through it. I'm going to use exactly the same technique as I used earlier. It's the same kind of question really, isn't it? You can see already. So let's put the data in. So we can work out the moles of NaOH, can't we? So that gives us 3.8565 times 10 to the minus 3 moles of NaOH. Now if we just pay attention to what it tells us that 2 acidic hydrogen atoms per molecule is the case for acid A. So therefore from the equation, or at least from that information, we can say that the mole ratio of A to NaOH is 1 to 2. So what we've got to do is divide 3.85675 to the 10 to the minus 3 by 2. But that's in 25 centimetres cubed. In 250 centimetre cubed, you have 10 times as much, same as before. So now we need to work out the molar mass of the compound. So that gives us 146 grams per mole to the minus 1, which allows us to say adipic acid is the acid in the chocolate mousse. Okay, so final question. So working on the same idea as before, nitric acid being a strong acid, you can assume that the concentration of hydrogen ions is the same as the concentration of the original nitric acid. So you can just sub in 0.015. So that gives us 1.82. So then it says the student diluted the nitric acid with an equal volume of water. So to do this final bit, you have to just think for a second, what does an equal volume of water mean? It means, actually, half the original volume, half the original concentration of HNO3. Let me say it again. An equal volume of water means the volume is now double. Same number of moles of HNO3 as before, so that means the concentration must have gone down. So volume and concentration are inversely proportional. So that gives us 7.5 times 10 to the minus 3 moles per decimeter cubed is the new hydrogen ion concentration. So that gives us a new pH of 2.12. So lower hydrogen ion concentration, slightly less strong acid, so the dilution effect actually has an impact on the pH as well. Okay, so that takes us to the end of the clip. Hopefully it's been fairly useful as a roundup.
So once again, thanks for listening, and until next time, see you soon.